Welcome. Let this be the only place you need to be tonight. Let your breathing loosen, your shoulders sink, and the weight of the day settle into whatever is holding you. There is nothing to do now but listen and let yourself drift. Tonight we follow the moon and the sea that answers it across 238,000 miles of open dark. That is the average distance between us and that pale, patient stone. Moon and Earth formed together from a single violent collision. Long before either had a name, a young planet roughly the size of Mars struck the newborn Earth. Debris from that impact spun outward into orbit and slowly gathered itself into a companion world. What we see tonight rising over the water once flew apart as fire and stone. It has been circling ever since. Every year, the moon drifts a little farther from Earth. The distance grows by about 1.5 inches annually, small enough to ignore in a single lifetime. Over millions of years, though, the gap widens noticeably. The moon our ancestors watched hung closer than the one above us now. It is, in its own way, always leaving, ever so slowly. Earth's oceans cover most of the planet's surface. Water spreads across roughly 70% of the globe, a thin blue skin over rock. Seen from space, our world looks less like land with water, and more like water with land. That balance is easy to forget from the shore, but it shapes almost everything that follows tonight. Gravity reaches across empty space, with no need for a medium. It needs no air, no wire, no touch of any kind. Between the moon and the Earth lies a stretch of vacuum, silent and airless, and still the pull crosses it without pause. Nothing has to travel through that gap for the attraction to be felt. It is simply there, holding the space between two worlds. The moon's tug on Earth is real, though astonishingly gentle. A person standing outdoors feels no tug at all, no shift in their own weight. The pull that moves oceans is a fraction of what gravity does to hold you to the ground. It is a small force, patiently repeated. Over the whole planet, though, small forces add up into something the sea cannot ignore. Water yields to gravity more easily than solid rock does. Stone holds its shape under strain, resisting slight pulls with quiet stubbornness. Water has no such stiffness. It flows toward whatever tugs at it, however weakly, however far away. That difference alone is why the sea moves to the moon's rhythm, while the mountains beneath it barely stir. Ocean water bulges upward on the side of Earth facing the moon. Drawn by that faint, steady pull, the sea rises just slightly higher there than elsewhere. It is not a wave crashing forward, but a slow swelling, spread across thousands of miles. From space, it would look like the faintest stretch in the ocean's shape. From the shore, it simply arrives as the tide coming in. At the very same moment, a second bulge rises on Earth's far side. It appears on the side of the planet turned away from the moon entirely. Two swellings exist together, one near, one distant, both part of the same quiet exchange between worlds. Together they explain why most shores greet two high tides, not one, in the course of a single day. Inertia, not the moon's pull, explains that far side bulge. Earth itself is pulled toward the moon slightly more strongly than the ocean on its far edge. That distant water lags behind, left slightly outward as the planet is drawn forward. It is not reached for, it is simply left in place, and so it rises. A quiet consequence of motion rather than a direct embrace. Let your breath find its own slow tide tonight. Breathe in and hold nothing tight. Let the exhale run a little longer than the inhale, spilling out like water down a shore. There is no rhythm to force here, only one to notice. Each breath arriving, each breath receding. Let your shoulders sink with the next release. Let your jaw loosen. You can simply keep breathing, and let sleep arrive the way the tide arrives, without hurry, without announcement. Earth turns beneath its two ocean bulges roughly once every day. The bulges themselves stay lined up with the moon, barely shifting position. It is the planet that rotates through them, like a slow wheel turning beneath two fixed lanterns. A given coastline passes through a bulge, then through open water, then through the second bulge, then back again. That single rotation is what turns a steady pull into a rising and falling shoreline. Two high tides and two low tides visit most coastlines every single day. This comes directly from passing through both bulges during one full spin. A shore rises, falls, rises again, falls again, all within about a day. Fishermen along such coasts grow up knowing this rhythm before they know the reason for it. The sea simply keeps its appointment, morning and night alike. 12 hours and a bit separate, one high tide from the next. Not exactly 12, a little more, always a little more. That small extra stretch comes from the moon's own steady drift across the sky. Sailors learned long ago to expect the tide a touch later each time, never quite on the hour before. Over a full day, those small delays add up to something noticeable. Each day, the tide arrives a little later than it did the day before. This delay follows the moon itself, which rises later and later as it moves along its own orbit. High water that came at noon today might come near 12:30 tomorrow. Coastal almanacs have tracked this drift for centuries, printed in patient columns of numbers. The sea, in this way, keeps the moon's calendar rather than the sun's. Isaac Newton first showed that ordinary gravity could account for the tides. Before him, the swelling and sinking of the sea had no accepted physical cause. Newton connected the falling of objects on Earth to the pull between any two masses, however distant. Applied to the moon and the ocean, the mathematics simply worked. What sailors had always felt in their bones became, at last, a solvable equation. In 1687, Newton published his law of universal gravitation. That single law tied the fall of an apple to the rise of the sea and to the orbits of planets besides. It stated plainly that every mass draws every other mass toward it. Applied to the heavens and the shore alike, it needed no separate rules for either. One quiet law, reaching from an orchard to an ocean. Long before Newton, Johannes Kepler guessed that the moon pulled the sea, and he was mocked for it. Writing in the early 1600s, Kepler suggested the ocean answered the moon's presence the way a magnet answers iron. His contemporaries found the idea fanciful, even embarrassing for an otherwise careful astronomer. It would take decades before anyone gave that hunch a proper mathematical home. Kepler did not live to see himself proven right. Galileo dismissed Kepler's tidal idea entirely, favoring an explanation built on Earth's own motion instead. He believed the sloshing of ocean basins came from the planet's rotation and orbit, not from any pull exerted by the moon. His reasoning was careful, but it missed the mark. Even brilliant minds, working without the right tools, can walk confidently past the correct answer. It sat waiting nearby the whole time. Sunlight is not the only pull on Earth's oceans. The sun tugs at them too, though far more faintly. Its mass is enormous, but its distance dilutes that strength considerably by the time it reaches the sea. Roughly, its tidal effect comes to less than half of what the moon manages here on Earth. Still, that fainter pull matters. Paired with the moon's, it shapes some of the ocean's largest and smallest swings. Spring tides arrive when the sun and the moon align, their pulls joining into one stronger tug on the sea. This happens twice each month, whether the moon sits new and dark or full and bright. When both bodies pull along the same line, their forces add together rather than compete. Higher tides climb further. Lower tides retreat further out, leaving wider stretches of sand exposed to the air. Feel the weight of your body settling into the mattress now, one part at a time. Let your feet grow heavy first, sinking softly into the sheets below them. Let that heaviness climb slowly upward, into your calves, your knees, resting there without effort. Your arms follow next, growing loose and full, as though gravity itself has finally been given permission to hold you. There is only the mattress beneath you, and the dark around you. At right angles, the sun and moon pull the sea in two different directions at once. This happens when the moon reaches its quarter phases, half lit from Earth's view. Their forces work against one another instead of adding. Highs fall short. Lows rise higher than they otherwise would. Sailors call this milder rhythm a neap tide. Highest highs and lowest lows both belong to spring tides. Along many coastlines, this means water climbing several extra feet up the beach, then retreating just as far below its usual mark. Tide charts mark these days with wider numbers. Coastal engineers plan around them. Fishermen watch them closely. For a few days near each new and full moon, the ocean simply reaches further in both directions. That word, spring, in springtide, has nothing to do with any season at all. It comes instead from an old sense of the word, meaning to leap or to burst forth, the way a spring of water rises from the ground. Sailors used the term long before anyone tied it to March or September, not the season. A spring tide can arrive in deep winter just as easily as in June. Full moons and new moons both bring spring tides, arriving twice within a single month. At full moon, Earth sits between sun and moon. At new moon, the moon sits between Earth and sun. Either arrangement lines the three bodies up along nearly the same stretch of space. The ocean cannot tell the difference. It only feels the combined pull and rises accordingly. A quarter moon marks the milder, more modest neap tide. When the moon appears half-lit in the sky, exactly a quarter of the way through its cycle, its pull works against the sun's rather than with it. Fishermen along many coasts expect smaller swings during these days. The difference between high and low water shrinks. Boats sit evenly in their berths. It is the ocean's version of an easy week. Tidal range differs enormously from one coastline to the next, even under the very same moon. Some shores rise and fall by only inches across an entire day. Others swing through many feet, exposing wide flats of sand and rock. Geography decides much of this difference: the shape of a bay, the depth of a channel, the width of a continental shelf. The moon pulls the same everywhere. The land answers each place differently. Bay of Fundy in Canada holds the largest tidal range found anywhere on Earth. Its long, narrowing shape acts like a funnel. It gathers water inward, pushing it higher than any other coastline the ocean touches. Ships that float easily at high tide can rest on exposed mud only hours later. Locals have long organized daily life around this rhythm, timing work and travel to match the water's reach. Few places compare. Water there can rise and fall more than 50 feet between tides, higher than a 4-story building sliding up and down twice a day. Wharves built along the bay include ladders bolted to their pilings, so boats and their crews can climb down to meet the falling water. Visitors sometimes stand on the same dock twice in one afternoon and see two entirely different shorelines. The change happens gradually enough to watch and fast enough to remember. Enclosed seas like the Mediterranean barely notice the moon at all. Their entrances to the wider ocean are narrow, and the water inside cannot rise or fall in step with anything happening beyond those straits. A sailor docked in Venice or Athens might watch for days without seeing much change. The pull from the moon still reaches every drop. The sea there simply has too little room to answer it. Ocean basins respond to the moon the way a bathtub responds to a nudge. Push water gently at one end, and it sloshes back and forth in its own natural rhythm, long after your hand has stopped moving. Every basin, large or small, carries a rhythm like this, built into its shape. The moon supplies the nudge. The basin decides how the water answers. Somewhere beyond the window, a hum rises and fades, a furnace settling, or wind finding a gap in the wall. It arrives without asking anything of you, and it leaves the same way. Your body doesn't need to track it. Let it come, let it go. The way a house breathes through a long night. Your shoulders can stay heavy where they rest. Nothing out there requires an answer from you. Every basin has a shape and size that decide how strongly it echoes the moon's pull. A wide, shallow basin might barely respond at all. A long, narrowing one can gather that same small push and swell it many times over. Depth matters too. Along with the length of the coastline, the water travels. The moon's tug never changes. The basin's geometry decides how loudly it answers. This echoing effect is called resonance, and it explains why Fundy grows so extreme. The bay's natural rhythm happens to match, almost exactly, the timing of the incoming tide. Each new wave arrives just as the last one is settling back, adding its strength rather than working against it. Over and over, the water builds. Nowhere else on Earth does the timing line up so perfectly. The Bristol Channel in England shares a similar resonant shape. It narrows as it stretches inland, funneling water, much as Fundy does, though on a smaller scale. Towns along its edge experience some of Britain's largest tidal ranges, with mudflats stretching wide at low water and vanishing within hours. Sailors there have long planned their crossings around the channel's particular rhythm. Some islands in the mid-Pacific see barely a foot of tidal change across an entire day. Far from any continental shelf, surrounded by deep open water, their shores rise and fall so gently that visitors sometimes never notice at all. The same moon hangs above them as above the Bay of Fundy. The ocean around them simply has no basin shaped to answer it strongly. Tidal bores form when an incoming tide pushes upstream against a river's own current. Instead of rising smoothly, the sea arrives as a single moving wall of water, forcing its way against the river's natural flow. The two currents meet and struggle, and for a while the river seems to reverse itself entirely, carrying the ocean's rhythm far inland. The Qiantang River in China produces one of the world's most famous tidal bores. Twice each day, a churning wall of water surges up its widening mouth, moving faster than a person could outrun it. The river's funnel-like shape gathers the incoming tide and squeezes it into this single advancing wave. Farmers and fishermen along its banks have long timed their work around its arrival. Crowds have gathered on its banks for centuries to watch the wave arrive. Old paintings and poems describe the same spectacle travelers still see today, a line of churning water rolling steadily upriver. Some come to admire it, others to fish in its wake, and generations of children have grown up knowing exactly which afternoons to watch the water rise. Tides lag behind the moon's position because oceans cannot respond instantly. Water is heavy, and moving such vast volumes of it takes time. Even as the moon glides overhead, the bulge it draws upward trails behind, still catching up. This gap between cause and visible effect shows up wherever tides are measured. It never fully closes. Friction between water and the seafloor slows the tidal bulge's response. As tides move across shallow shelves and rocky channels, drag holds them back. Deep ocean water flows with far less resistance than water crossing a cluttered coastal bottom. Reefs, sediment, and headlands each add their own small resistance. The bulge arrives late, dragging its heels behind the moon. This lag is called the tidal phase, and it varies by coastline. Two harbors only a few miles apart can experience high tide hours apart. Local depth, shape, and the angle of the coast all shift the timing. Sailors learn their own harbor's phase the way they learn a familiar face. No formula alone replaces that local knowledge. Let a small warmth begin near your hands, wherever they happen to rest. Feel it spread up through your wrists, into your forearms, loosening anything they were still holding. It moves into your shoulders next, easing them down and back. From there, it drifts into your chest, rising and falling with each breath, taking its time. Let it keep traveling wherever it wants to go. Early sailors on the Mediterranean barely noticed tides and rarely wrote about them. Their sea is nearly enclosed, its tidal range so small it hardly registers on open shorelines. A fisherman working those waters might live a whole life without once naming the word tide. Their accounts speak of wind and current, almost never of rising and falling water. Pythes of Massalia, sailing north around 325 BC, was among the first Greeks to record ocean tides. He journeyed far beyond his home waters, past coasts most of his countrymen never saw. Reaching Britain, he watched water rise and fall by heights unlike anything in his own sea. He wrote down what he saw, carefully, though he understood little of the cause. His accounts of Britain's tides were doubted by scholars for centuries afterward. Writers back home found his descriptions strange, even implausible, since nothing in their own waters resembled them. Some dismissed him outright as a teller of tall tales. Only later, as more travelers reached those same shores, did his account begin to seem less like invention and more like careful observation. Chinese scholars linked tides to the moon's phases long before Newton's calculations existed. Writings from many centuries past describe a clear relationship between the moon's changing face and the sea's rise and fall. These observations were practical, drawn from watching harbors and rivers over long stretches of time. No equations accompanied them, only careful record, keeping across many generations. Seleucus of Seleucia, an astronomer working around 2,000 years ago, connected tides to the moon's motion. He proposed that the sea answered the moon, the way a shadow answers the sun. His reasoning has not survived in full, only fragments quoted by later writers. Even so, his instinct pointed toward something true, long before anyone could prove it mathematically. Medieval sailors along the Atlantic coast built their lives around tide timing. Harbors emptied and filled on schedules that decided when boats could leave and when they had to return. Fishermen read the water the way farmers read seasons, shaping each day's work around its rhythm. Missing a tide could mean missing a harvest or being stranded on an exposed shore until the water came back. Pierre-Simon Laplace developed the first full mathematical theory of tides in the late 1700s. He was a French mathematician working across astronomy and physics. Newton had shown why tides exist, but not how they moved once currents and coastlines complicated the picture. Laplace built equations that could follow the ocean through time. His work turned tides from an idea into something calculable. Laplace's equations treated the ocean as a thin fluid shell wrapped around a spinning Earth. This simplification let him model the pull of the moon and sun as forces acting on that shell, rather than on any single point of water. The approach captured how depth, rotation, and current shaped the tide together. It was elegant. Oceanographers still recognize it as the foundation beneath every modern tidal calculation. William Thomson, later known as Lord Kelvin, built a mechanical tide predicting machine in the 1870s. Thomson was a physicist, fascinated by turning abstract mathematics into working devices. His machine translated Laplace's equations into brass gears, each one representing a different rhythm of the tide. Turning a crank set the whole assembly moving. From its motion, a pen traced the rise and fall of water still to come. Kelvin's machine used gears and pulleys to forecast tides years in advance. Each gear spun at its own steady rate, matching one of the ocean's many overlapping rhythms. Together, their combined motion drew a smooth curve across paper, tracing high water and low water long before either arrived. Sailors and harbor masters trusted these predictions completely. A room full of turning brass had learned to speak the sea's own language. Somewhere past the window, a candle burns low in its dish, the flame narrowing until it is little more than a bead of orange light. Watch how it steadies before it fades, never rushing toward the dark. Your own thoughts can borrow that pace tonight, thinning slowly without needing to disappear all at once. There is no hour to keep. Let the small light inside you dim in its own time and rest there. Tide predicting machines were once essential tools for every major port. Before satellites and computers, harbors depended on these brass calculators to plan shipping schedules months and even years ahead. A missed prediction could strand a vessel on a sandbar or waste an entire tide's worth of cargo loading. Ports across Britain, France, and beyond kept their own machines running quietly in back offices. Commerce itself moved to the rhythm those gears produced. Harmonic analysis breaks the tide into simple repeating rhythms that can be summed together. Each rhythm corresponds to a particular motion in the sky, the moon's orbit, the sun's path, the small wobbles in both. Individually, these rhythms look like plain, gentle waves. Added together in the right proportions, they recreate the tide's full complexity. It is a kind of musical chord, written in water instead of sound. Modern tide tables still rely on this harmonic method, refined by computers now. The core idea from Laplace's era remains unchanged, only the calculating has grown faster. Where Kelvin needed brass and cranks, today's forecasters need only a few seconds of processing time. Coastal agencies publish tide predictions years into the future with remarkable accuracy. The ocean's rhythm, once traced by hand, now arrives instantly on a screen. A tide gauge in Brest, France has recorded sea level continuously since 1711. Built along the harbor wall, it has measured the rise and fall of water through wars, storms, and centuries of changing technology. Few instruments anywhere have run for so long without interruption. Each mark on its record adds to a story, written one tide at a time. The gauge itself has outlived the people who first installed it. That single gauge became one of the longest unbroken records in ocean science. Researchers studying sea level today still reach back to its earliest entries, comparing centuries of water height against one another. Few places on Earth offer such a continuous thread through time. The record shows tides behaving with remarkable consistency, decade after decade. It stands as a quiet testament to patient, careful observation. Long before anyone measured a tide with instruments, coastal families learned its rhythm by watching the shore itself. A grandmother could tell, by the color of wet sand, how many hours remained before the water returned. Children grew up knowing which rocks stayed dry and which vanished twice a day. No equation guided them, only years of careful noticing. Their knowledge came from the shore, not from a page. Shellfish gatherers still move with the falling tide, a habit far older than writing itself. As the water pulls back, they follow it across the flats, baskets in hand, reading exposed mudbanks like a map. Clams and cockles surface only in that narrow window of low water. Wait too long, and the sea reclaims its ground. Their timing is inherited, not calculated. This tidal knowledge passed from parent to child, long before it wore the name of science. Stories, songs, and simple sayings carried the pattern forward without ever needing formulas. A saying about the moon's shape might quietly encode when the fish would run. Only much later did scholars write down what fishing families had always practiced. The sea's rhythm lived first in memory. Between the reach of high water and the reach of low water lies a narrow strip called the intertidal zone. Twice each day, the sea uncovers it, and twice each day, the sea claims it back. Life there exists in two entirely different worlds, submerged and exposed, within a single afternoon. Few places on Earth shift so completely, so often. The shoreline itself seems to breathe. Barnacles solve the problem of that shifting world by simply not moving at all. Each one cements itself to a rock in youth and stays there for life. When the tide falls, it seals its shell tight and waits. When water returns, tiny feathery limbs unfurl to feed. Patience, for a barnacle, is the entire strategy. Let your face soften now, the way a held expression finally lets go. There is no need to hold your eyebrows steady or your jaw set in place. Let them loosen, the smallest fraction at a time. Behind your closed eyes, there is only warm darkness, wide and unmeasured. Let your eyelids grow heavier than they have felt all day. Nothing waits behind that darkness but rest. Mussels handle low tide differently, clamping their shells shut to trap a small reserve of seawater inside. That sealed pocket keeps their tissue moist through hours of open air. Packed together in dense clusters, they shield one another from drying wind and sun. Their closed shells look still, almost lifeless. Inside, though, they are simply waiting out the hours until the sea comes home. Every rise of the tide refills the small basins scattered across a rocky shore, and each one becomes a world of its own. Anemones sway, tiny crabs sidestep along the edges, minnows dart between fronds of weed. For a few hours, that pool holds its own temperature, its own light, its own quiet drama. Then the tide rises again, and everything is renewed. Anemones respond to the falling water by folding inward, drawing their soft tentacles into a tight, glistening knot. What was open and flowing becomes a small, closed dome on the rock. This protects their delicate tissue from drying air and hungry gulls above. Once the tide returns, they slowly unfurl again, patient and unhurried in their own quiet way. The cycle repeats without complaint, tide after tide. Crabs choose a different shelter, retreating into damp crevices and beneath loose stones as the water withdraws. There, cool shadow and residual moisture protect them from the drying air above. Some burrow into wet sand instead, tucking themselves just beneath the surface. Hours pass in stillness until the returning tide reaches their hiding place. Then they emerge, unhurried, back into open water. Horseshoe crabs choose the highest spring tides of the year for their mating rituals. Along Atlantic beaches, thousands crawl ashore together when the water reaches its farthest edge. Males cling to females as waves push them toward soft sand. Their timing has stayed unchanged for tens of millions of years. Long before dinosaurs, this same lunar rhythm brought them to shore. Grunion fish strand themselves on California beaches during a handful of chosen spring tides. Riding the last surge of water, females wriggle into wet sand to bury their eggs. Males curl around them, releasing milt as the wave withdraws. Both fish must catch the very next wave back to sea. Their entire spawning window lasts only minutes, timed by the moon alone. Great Barrier Reef corals often spawn together, following the same lunar rhythm as the tide beneath them. Once a year, after sunset on particular nights, countless coral colonies release eggs and sperm within the same short window. Warmer water and moonlight seem to set the trigger, though the exact cue remains only partly understood. The ocean briefly fills with drifting pink clouds. Then the water clears, and the reef returns to stillness. Sea turtles time their climb up the beach to coincide with high tide. Rising water shortens the distance they must drag their heavy bodies across open sand. Predators have less time to notice them under cover of surf and darkness. Once above the tide line, a turtle digs her nest and lays her eggs. She returns to the sea before the water pulls away again. Migratory shorebirds plan their feeding around the falling tide. As water retreats, mudflats and sandbars emerge, thick with worms, crabs, and tiny mollusks. Flocks descend the moment the ground appears, probing quickly before the sea returns. Their whole migration schedule bends around this rhythm, thousands of miles from breeding grounds to feeding shores. Few travelers depend so precisely on the sea's own clock. Mangrove forests depend on tidal flooding to survive along the world's warm coastlines. Incoming water carries nutrients deep into the tangled roots, feeding soil that would otherwise starve. The same tide, retreating hours later, flushes away excess salt that would poison ordinary trees. Mangroves have adapted to thrive exactly within this push and pull. Without the tide's steady visits, their entire ecosystem would slowly collapse. Notice how your breath has already begun to slow, without any effort from you. Each inhale arrives a little smaller now, each exhale a little longer than the one before it. There is a natural pause between them, a soft hollow of stillness. Let that pause widen just slightly with every breath you take. Your shoulders have nowhere left to climb. Let them rest exactly where they are. Salt marshes breeze with the tide, filling and draining on a steady daily cycle. High water spreads across the grasses, depositing silt and feeding the roots below. As the tide falls, channels drain the marsh, carrying nutrients out toward open water. This rhythm shapes every creature living within the marsh, from fiddler crabs to nesting birds. The whole landscape rises and falls, like a slow, living lung. Moon jellyfish drift wherever the current carries them, offering little resistance of their own. Their pale, translucent bodies pulse gently, but true movement comes from the water around them. Tidal currents, generated in part by the moon's pull, sweep them along coastlines and into bays. Vast numbers can gather wherever these currents converge. Watching them, it seems the sea itself decides where they belong. Tidal currents move staggering volumes of water without any wind pushing them at all. Twice a day, the sea surges into bays and estuaries, then withdraws just as completely. In narrow channels, this movement can rival the flow of the world's largest rivers. No storm drives it, no wind stirs it. Gravity alone, reaching down from the moon, keeps this immense flow turning. Estuaries live where river meets sea, and the tide does most of the mixing. Fresh water pours down from inland, lighter and less salty. Twice a day, the tide pushes seawater upstream, folding the two together. This constant stirring creates some of the richest nurseries on Earth. Without that tidal pulse, the layers would barely blend at all. Venice sits low against the Adriatic, and its canals answer to the same pull as any open coast. Visitors strolling over stone bridges rarely notice the water creeping higher against the walls. Gondoliers feel it more, adjusting their poles as the level shifts through the day. The city's foundations were built with this rhythm already in mind. Beneath the postcards, an ordinary tide keeps time. Venice has spent centuries answering to what locals call acqua alta, the high water that floods its squares. Storms and unusually strong tides can push the sea over the canal walls entirely. St. Mark's Square becomes a shallow lake more often than tourists expect. Wooden walkways appear overnight to keep foot traffic above the flood. The city has learned to live with water that occasionally refuses to stay in its channels. Harbors are built around the tide's own schedule, not against it. Engineers study decades of records before laying a single stone. Locks open and close at calculated windows, letting ships pass only when the water sits at the right height. A harbor mistimed against the tide can strand vessels in mud for hours. Good design simply listens to a rhythm that never misses a beat. Sailing ships once lived and died by the outgoing tide. Captains watched the water fall, knowing it would carry them out past the harbor mouth without a struggle. Missing that window meant waiting half a day for the next. Old logbooks record departures, timed almost to the minute. The sea, in this sense, decided when a voyage truly began. History remembers a handful of naval battles where the tide, not the cannon, decided the outcome. Ships trapped on a falling tide could run aground before a single shot was fired. Commanders who understood the local currents held a quiet advantage over rivals who did not. Fleets have been delayed, stranded, or freed entirely by water no one controlled. Even warfare, it turns out, deferred to the moon. The moon's pull explains the rise and fall, but it does not work alone. Earth itself spins beneath the two bulges, once every day, carrying them along for the ride. This rotation bends the simple picture of gravity into something more intricate. The ocean's response depends as much on the planet's turning as on the moon overhead. Two motions, working together, shape every tide that reaches shore. Let your body grow heavier now, starting at your feet. Feel them press a little deeper into the sheets, as if the mattress were slowly rising to meet them. That same weight climbs into your ankles, then your calves, settling like sand through water. Let your knees soften under it, then your hips, sinking further with each breath. By the time it reaches your chest, you may hardly remember choosing to lie still at all. Earth turns faster than the tide can keep pace with, so the ocean's bulge drifts slightly ahead of where the moon actually sits overhead. Friction with the seafloor drags this mound of water forward, just a little, with every rotation. The mismatch is small, but it never disappears. That small offset carries consequences far beyond the shoreline. It reaches all the way out to the moon itself. That forward-leaning bulge carries its own gravity, faint but real, and it tugs back on the moon as it passes. The pull nudges the moon forward in its orbit, ever so slightly, and a forward nudge means a wider path. Orbit by orbit, the moon eases a little farther from Earth. The distance grows by roughly the width of a fingernail each year. Across enough years, that quiet nudging has carried the moon thousands of miles farther than it once orbited. Rotation itself pays a small price for that tug on the moon. As the bulge pulls back on Earth's spin, it drains a sliver of rotational energy with every turn. The effect is tiny, measured in fractions of a second across a whole year. Still, it adds up. Across deep time, Earth's day has been getting longer, one imperceptible moment at a time. Hundreds of millions of years ago, a day on Earth lasted several hours less than it does now. The planet spun faster, so sunrise and sunset chased each other more quickly across the sky. Creatures living then, had they kept clocks, would have measured shorter mornings and shorter nights alike. Nothing about the planet's size changed, only its spin, easing with each passing age. Fossilized coral holds a record most people never think to look for. Each coral animal added a thin layer of skeleton daily, leaving faint ridges like the rings of a tree. Counted closely, those ridges can reveal how many days once filled a single year. The lines are delicate, barely visible without magnification. Yet within them sits a quiet ledger of a faster-turning Earth. John Wells, a geologist, sat with fossil coral slices in 1963, counting their faint daily lines. He tallied the growth rings across a full year's worth of coral skeleton, layer by layer. His count came out higher than the current number of days in a year. That difference was no error. It matched what physics had already predicted, but never proven, about Earth's slowing spin. His fossil measurements offered some of the earliest physical evidence that Earth's rotation has been slowing for ages. Before him, the idea rested mostly on calculation and theory. Coral gave it a tangible trace, etched in stone. Scientists in other fields soon looked for similar clues, in tree rings, in ice, in ancient tidal deposits. A humble sea creature had quietly confirmed a cosmic process. Tidal friction converts a small amount of Earth's spinning energy into heat with every rotation. Water dragging against the seafloor and the seafloor dragging against the water. Both generate warmth from that constant motion. The amount is modest compared to Earth's total heat budget. Even so, it never stops. Day after day, the ocean's endless sliding motion quietly does its small thermal work. That heat disperses into the ocean and the solid earth beneath it, spreading far too thin to notice. No patch of seafloor grows warm to the touch because of it. The energy scatters into currents, into rock, into the vast heat-absorbing body of the planet itself. Nothing dramatic marks its passage. It simply joins the slow thermal breathing of a world always in motion. Moonrise arrives about 50 minutes later each following night. The moon does not orbit in step with Earth's daily spin, so its appearance above the horizon keeps drifting later, evening after evening. Watch across a week, and moonrise creeps well past its earlier hour. Across a month, it circles through nearly every hour of the clock. The sky itself keeps time to a rhythm distinct from the sun's. Somewhere beyond these walls, a low hum rises from a passing car, then fades back into stillness. It comes and goes, without asking anything of you. Notice how easily it leaves again, how the room settles back around it. Your shoulders can settle the same way, loosening a little more with each sound that arrives and drifts off. Nothing needs holding. Everything you hear is already passing through. That daily lag defines what tide watchers call a lunar day, a little longer than an ordinary solar day. A solar day runs the familiar 24 hours, measured by the sun's return overhead. A lunar day stretches roughly 50 minutes beyond that, matching the moon's slower return to the same point in the sky. Tide charts follow this lunar rhythm, not the sun's. It is the moon's own clock, quietly running beneath ours. Two gravitational voices speak to the ocean at once, the moon's and the sun's. When their timing aligns, their pulls add together, lifting spring tides higher than either could alone. When their timing works against each other, the pulls partly cancel, leaving neap tides milder and less pronounced. The sea never hears one voice alone. It always answers a duet, shifting balance night after night, month after month. Along the Pacific coast, tides arrive mixed. Each day brings two high tides, but rarely of matching height. Morning's crest often rises above afternoons, then the pattern shifts again the next day. This unevenness comes from lunar and solar influences overlapping at that latitude in a particular way. San Francisco Bay charts show the pattern clearly, printing two unequal peaks day after day. Certain stretches of the Gulf of Mexico feel only one high tide and one low tide daily, not two. This pattern is called a diurnal tide, simpler in rhythm than most coastlines experience. Pensacola and parts of the Florida Panhandle show this clean, single cycle. The moon still pulls twice a day, but shallow geometry and local resonance erase one of the pulses. Only one rhythm remains, steady and singular. Atlantic coastlines mostly follow a semidiurnal pattern, two high tides and two low tides of nearly equal size each day. Boston Harbor and the coast of Maine both show this even rhythm clearly. High tide arrives, water recedes. Another high tide follows roughly 12 hours later, almost matching the first. It is the tide most people picture when they imagine the sea's daily motion. Reliable, balanced, and easy to predict. Which of these patterns a coastline experiences depends on the shape of its basin and its distance from the equator. A narrow, resonant bay might amplify one rhythm while suppressing another. Latitude shifts the balance between lunar and solar influence in ways still being refined by oceanographers. No single rule predicts a coastline's tide from a map alone. Every shoreline earns its rhythm through its own particular geometry. Water is not the only thing the moon's pull deforms. Solid rock answers too, though far less visibly than the sea. Earth's entire body flexes slightly under lunar gravity, stretching and relaxing in the same rhythm as the tides offshore. The ground beneath a house, a forest, a city street, rises and falls with a motion too small for any hand to feel. Earth's crust lifts and settles by a few inches under the moon's daily pull, a motion called the solid Earth tide. Mountains rise almost imperceptibly, then ease back down, following the same daily rhythm as ocean water. No rumble accompanies it, no visible cracking. The continents themselves breathe with the moon, in a motion too gradual for any eye to catch. This solid Earth tide leaves no mark on the eye, no shifted skyline, no toppled fence post. Instruments buried deep in bedrock, though, register the motion precisely, tracing curves that match lunar timing exactly. Geophysicists rely on this hidden signal to study Earth's interior structure, since how much the ground flexes reveals something about what lies beneath it. Laboratories built for extreme precision keep gravimeters running day and night, devices sensitive enough to register the moon passing overhead. As lunar gravity tugs at the instrument's suspended mass, the machine records a rhythmic rise and fall matching the tide outside, even in buildings far from any coastline. Scientists once used these tiny fluctuations to check their models of the moon's orbit itself. Feel a small warmth rise across your shoulder blades now, the way sunlight settles on a stone wall left standing in late afternoon. Let it spread down each arm, loosening the space behind your elbows, reaching into your wrists. It asks nothing of you, only spreads where you let it. Let it pool in your fingertips and stay there, doing nothing more than being warm. Your whole body can rest inside that warmth tonight. Even the atmosphere feels a subtle tidal push from the moon overhead. Air itself, thin and restless, answers to the same pull that tugs at the sea. High above the clouds, gas layers lift by the smallest measure as the moon passes over. The effect stays far too small to sense on skin or breath. Instruments in orbit have traced it nonetheless, a whisper of gravity moving through open sky. Atmospheric tides are far weaker than oceanic ones, and mostly driven by sunlight instead. Heat from the sun expands and contracts the air across each day, a rhythm stronger than anything the moon manages up there. This solar heartbeat moves the whole atmosphere in a slow daily swell. Lunar gravity adds only a trace beneath it. Instruments tracking upper air currents find both signals layered together, one loud, one barely there. Lake Superior technically has tides, though they measure only a couple of inches. Its vast fresh water answers to the moon's pull, just like any ocean does. The rise stays small enough that wind and waves erase it entirely. No dock worker there has ever timed a delivery by it. Physicists have measured it anyway, proof that lunar gravity touches every body of water, however landlocked it seems. Most lakes are too small for any noticeable tidal bulge to form. A pond, a reservoir, even a modest inland sea lacks the width for gravity to build any real swell. The moon still pulls on every drop within them, but the distance across the water never grows long enough for the difference in pull to matter. Only oceans, and a very few enormous lakes, carry width enough to show it. The open ocean itself only rises about 1.5 feet from the tidal pull alone. Far from any coastline, the sea bulges upward by scarcely 18 inches, a rise a sailor might never notice from a rolling deck. That modest swell travels the whole width of an ocean basin. Its size stays constant across open water. Everything more dramatic that follows happens only once that water meets the shallows near land. Coastal tides grow far larger than open ocean tides because shallow water amplifies them. As the tidal bulge approaches land, the seafloor rises to meet it, squeezing the same volume of water into a narrower space. That squeeze forces the water higher against the shore. Bays and inlets shaped just right can multiply the effect many times over. A modest ocean swell becomes, in certain harbors, a rise measured in yards rather than inches. A tidal wave, in the true sense, has nothing to do with tsunamis despite the shared name. The phrase once described the ordinary swell of high tide moving into a bay or river mouth. Sailors and coastal residents used it for centuries. It carried no sense of danger. Somewhere along the way, the same words attached themselves to a far more violent kind of wave, and the confusion never fully faded. Tsunamis come from earthquakes or landslides, not from the moon at all. A sudden shift in the seafloor displaces an enormous volume of water all at once, sending it racing outward in towering waves. Gravity from the moon plays no part in that motion. The two phenomena share nothing but an old, misleading name. One unfolds over hours across an entire ocean basin. The other builds in seconds beneath the crust. Confusing the two names has caused misunderstanding among the public for generations. News reports once used tidal wave loosely for any destructive surge, blending a slow lunar rhythm with sudden geological violence. Oceanographers have spent decades trying to separate the two in public understanding. The word tsunami, borrowed from Japanese, now serves that purpose. Still, the old phrase lingers in memory, attached to images it never actually described. Tidal power stations capture the rise and fall of the sea to generate electricity. Engineers place turbines where tidal currents run strong and predictable, letting moving water turn blades much like wind does above ground. The sea provides the push. No fuel burns, no exhaust rises. Twice each day, without fail, the tide arrives to turn the machinery again. A rhythm engineers can set a calendar by. Somewhere in this room, a thin shaft of light holds a slip of dust, turning without hurry, neither rising nor falling. Let your hands rest like that now, weightless, going nowhere. Your jaw can loosen. Your shoulders can drop an inch you didn't know they were holding. Nothing asks anything of you tonight. Let the dust settle, and let yourself settle with it, drifting toward whatever comes next without needing to know its shape. La Rance, on the coast of Brittany, opened in 1966 as one of the first tidal power plants in the world. Engineers built a barrage across the river's estuary, letting the tide fill and drain a basin twice each day. Turbines set into the barrage still spin today. The plant proved a coastline could be harnessed without burning anything at all. Decades have passed. It still turns with the tide. Modern tidal turbines resemble windmills set beneath the waves, their blades shaped to catch moving water instead of moving air. Engineers anchor them to the seafloor in channels where currents run strong and steady. The tide pushes, and the blades turn, feeding a generator inside. Unlike wind, the current always returns from the same direction, twice a day on schedule. The machinery simply waits for it. Engineers value tidal energy because its rhythm can be forecast years in advance, unlike wind or sunlight. The moon's orbit is steady enough that tables can predict the tide's height at a given hour decades from now. Power planners use these tables to know exactly when a turbine field will produce its most electricity. No storm has to pass, no breeze has to rise. The sea simply keeps its appointment. Tide, the word itself, once meant simply time in Old English, as in noontide or eventide. Only later did English narrow it to the sea's rise and fall. Other languages kept a similar double meaning, tying the ocean's rhythm to the passage of hours. Language remembers this. The old sense still lingers beneath the modern word. Satellites equipped with altimeters now measure the height of the sea's surface across the entire globe, tracking bumps only inches tall from far above. These instruments bounce radar pulses off the water and time their return with extraordinary precision. Scientists compare the measurements against centuries, old tidal models to check their accuracy. The models hold up remarkably well. Space offers a clear view of the sea's oldest rhythm. A single tide prediction for one stretch of coastline can combine more than 30 distinct harmonic components, each representing a different rhythm from the moon, the sun, and Earth's own shape. Some repeat every 12 hours, others stretch across weeks or years. Added together, they produce the particular curve of highs and lows for that shoreline. No two coastlines match. The sea's local voice is written in that private mixture. Fishermen working tidal creeks still consult printed tide charts each morning before setting out, checking the hour of the next high water. A boat that leaves too early can run aground in mud the sea hasn't yet covered. One that leaves too late misses the window. The paper is creased from handling. It holds calculations older than anyone aboard. It tells them when the water will carry them home. Coastal cities such as London built massive barriers to hold back tides that rise unusually high, often driven by storms layered atop an ordinary spring tide. Engineers designed movable gates that could swing shut across an entire river, sealing the city off from the sea for a few critical hours. Such barriers protect homes, streets, and underground rail lines from flooding. They stand open most days, letting boats and water pass freely. They rarely close. London's Thames Barrier has closed against surging tides more than 200 times since its completion in 1982, each closure a small arithmetic of moon, storm, and river. Operators watch forecasts of wind, pressure, and tidal height converge before making the call. When the gates swing shut, the city behind them continues, unaware. The barrier was built to last well into this century. It waits, mostly, simply open to the tide. King tides sound dramatic, though they are simply the ordinary highest tides of the year, given a memorable name. They arrive when sun, moon, and earth align especially well, lifting an already high spring tide a little further still. Coastal towns post warnings. Watch water lap over familiar walls. Nothing new happens in the sky, only forces already known, gathered at their strongest angle, doing exactly what they always do. Let the small tension around your eyes dissolve now, the kind you carry without noticing through the day. Your jaw can loosen, teeth drifting apart, lips barely touching. Behind your closed eyes, there is only a low, shifting dark, asking nothing of you. Let your eyebrows drop, unclench, spread wide across your forehead. The whole face can rest. The way it rests, deep inside sleep, long before waking. Nothing needs your expression tonight. Perigean spring tides happen when an ordinary spring tide coincides with the moon's closest pass by Earth. Both effects stack together, sea rising a bit higher and falling a bit lower than usual. Harbor masters note the date, months ahead. Nothing violent occurs. It is simply two familiar rhythms, briefly overlapping, lending the sea a touch more reach than most days allow. Earth's constant companion does not circle in a perfect ring. Its orbit traces a gentle oval, drifting the moon nearer and farther across each month. At its closest point, the distance shrinks by tens of thousands of miles compared to its farthest. Sailors and skywatchers notice the moon looking slightly larger some nights than others. That subtle shift in shape quietly governs how strongly the sea gets pulled. At its closest approach, a point astronomers call perigee, the moon's pull on the sea grows a little stronger. Coastal waters climb slightly higher than average, retreat slightly lower too. The difference is measurable but never overwhelming. Ships' logs across centuries recorded these closer months without knowing the cause. It took careful orbital mapping to reveal why some tides simply reached a bit further than others. At its farthest point, called apogee, the moon eases its grip on the sea, though only slightly. Tides grow a touch smaller, never dramatically weaker. The ocean barely notices the difference from one week to the next. This modest give and take repeats every month, a quiet negotiation between distance and gravity that never swings to extremes. The sea simply breathes a little shallower for a while. 4.5 billion years ago, the newborn moon circled far closer to Earth than it does now, likely only a small fraction of today's distance. It had just formed from the debris of a great collision, still hot, still settling into shape. From Earth's surface, it would have filled far more of the sky. Its pull on the young ocean was correspondingly immense. Tides in that early ocean would have towered far higher than any coastline feels today, rising and falling with tremendous force each day. The young Earth also spun much faster then, so those towering tides arrived in rapid succession. No shore, no life, no witness existed yet to see them. Only water, rock, and a very close moon, locked in their first long conversation. Across unimaginable stretches of time, those towering tides slowly settled toward the familiar rhythm we know. Bit by bit, as the moon drifted outward, its pull loosened, and the sea's daily swing grew smaller and steadier. Hundreds of millions of years folded into the process, each one barely different from the last. What began as violence became routine, the ocean settling into the calm cadence still felt on shorelines tonight. Even now, the moon continues drifting outward, and it will keep receding for billions of years to come. Each year, the distance grows by only a sliver, far too small to notice in one lifetime, or 100. The tides will keep loosening their grip across that immense span, easing by degrees no one alive will ever measure. The sea will simply keep answering a voice that grows, ever so faintly, more distant. Billions of years from now, Earth's day and the moon's orbit may finally fall into step, each one matching the other's pace so precisely that the moon would hang above the same patch of ocean forever. That balance is called tidal locking, the same fate the moon long ago handed Earth, showing us only one face. Reaching it would take longer than the sun itself is expected to shine. It remains a distant, theoretical horizon. Should that balance ever arrive, tides would grow fainter than any felt today, their daily swing reduced to a whisper. Yet they would not disappear. The sun's own pull, however modest, would still tug at the water. A trace of rhythm would remain, however small. Let your exhale grow a little longer than your inhale now, just slightly, the way a wave takes longer sliding back than it took arriving. No counting required, no pace to keep, just that small lean toward longer breaths out, again and again, each one asking a little less of you than the last. Mars carries two small moons, Phobos and Deimos, yet neither stirs any meaningful tide across its dry, dusty surface. Both moons are tiny, more like captured rubble than true companions. Mars also has no ocean left to answer any pull. Its ancient basins sit silent, waiting on nothing. Far beyond Mars, Jupiter's moon Europa endures a far stronger conversation with its planet. Jupiter's gravity is immense, and as Europa circles, it gets stretched and squeezed with every orbit. The moon flexes like something breathing. This constant kneading leaves its mark deep inside. That endless flexing generates heat, and scientists suspect it keeps a vast ocean liquid beneath Europa's frozen shell. The ice above may be miles thick, sealing in warmth and darkness below. No sunlight reaches that hidden sea. Only tidal motion keeps it from freezing solid. Saturn's moon Enceladus takes this even further, venting plumes of water straight into space. Those jets erupt from cracks near its south pole, driven partly by the same tidal flexing Europa feels. Spacecraft have flown directly through the spray. Inside those droplets, salts and organic traces have been found drifting in the dark. A giant planet's pull can warm a small moon's interior for eons, long after any leftover formation heat would have faded. Without a large neighbor tugging rhythmically, a moon that size should have frozen through ages ago. Tidal flexing keeps the furnace lit instead. It is patient heating, born of nothing but repeated stretching. Earth's own tides, set beside these distant worlds, move mostly water rather than rock and ice. Our planet's crust flexes only slightly under the moon's pull, nothing like Europa's endless kneading. The ocean absorbs nearly all the motion instead. It is a gentler arrangement, suited to a world already so wet. Astronomers now search other star systems for the tidal fingerprints hidden moons might leave behind. A planet's light can flicker or wobble in patterns that hint at an unseen companion tugging nearby. No confirmed ocean tide beyond our solar system has yet been found, but the search itself carries the same quiet patience the tides have always kept. No spacecraft has yet confirmed an ocean tide anywhere beyond our solar system. The instruments we build can catch a planet's wobble or a shadow crossing a distant star, but a tide hides deeper than that. It would take a moon, an ocean, and exactly the right angle of view. For now, the search continues without an answer. The absence of proof is not the same as absence itself. Coastal communities today still plan festivals, harvests, and ceremonies around tidal timing. Fishing villages set their calendars by the falling water rather than the clock on the wall. Temple processions along certain shores wait for a particular low tide to cross a causeway. Harvest days for shellfish or seaweed follow the same old arithmetic of moon and sun. The rhythm that shaped ancient life still shapes modern schedules. Fishermen in the Philippines time Bangus fry, gathering to the pull of certain tides. Milkfish larvae ride the incoming water toward river mouths and shallow lagoons. Villagers wait with fine nets at the exact hour the current favors them. Miss the tide, and the fry slip past unseen. Generations of practice have turned this timing into quiet, dependable knowledge. Let your body rest heavier now, as though the mattress has grown a little softer beneath you. Feel that heaviness begin at your shoulders, sinking first, releasing whatever they carried through the day. Let it spread down through your arms, into your hands, until even your fingers feel unwilling to move. Your hips settle next, heavier still. Then your legs, then your feet, each one giving its small weight to the bed below. There is only this slow settling, one part following another, nothing asked of you but to let it happen. Pacific Island navigators once read subtle tidal swells to help find their way at sea. Long before compasses reached these waters, sailors felt patterns in the swell that told them an island lay ahead, unseen past the horizon. Certain wave shapes bent around distant land and carried that bending for miles. Skilled navigators learned to feel these signs through the hull of a canoe. It was a form of reading the ocean's memory of the shore. Traditional Hawaiian fish ponds were engineered to trap fish using the ebb and flow of tides. Stone walls, built along the shallows, allowed small fish to swim in with the rising water. Sluice gates, called makaha, let the tide pass through while keeping larger fish inside as they grew. Communities tended these ponds for generations, harvesting without ever needing nets. The design relied on nothing but patience and the moon's steady pull. Tide pools remain a favorite place for children to first encounter the rhythm of the sea. A single afternoon at low tide can reveal a universe of small creatures tucked into rock crevices. Sea stars cling motionless, anemones bloom and close, hermit crabs shuffle between shells. For many people, this is the first proof that the ocean has a schedule at all. Curiosity begins in shallow water, cupped hands and bare feet on wet stone. Marine biologists study tide pools because their conditions shift more than almost any habitat on Earth. Temperature can swing sharply between a sunlit low tide and the cool rush of returning water. Salinity rises as puddles evaporate, then falls again with the next flood. Oxygen levels drift with both heat and time. Creatures here endure a daily test that few other environments demand. The gravitational bond between Moon and Earth has shaped biology since life first reached the shore. Long before anything walked on land, the intertidal zone offered a border between two worlds, wet and dry, twice each day. Organisms that could tolerate this repeated exposure found room to adapt in ways calmer waters never demanded. Evolution favored resilience at the water's edge. The tide, in its quiet way, has been teaching life to endure change for a very long time. Early tidal pools may have offered the shifting conditions where life took its first steps, or so certain biologists suspect. Repeated wetting and drying could have concentrated simple molecules, bringing them close enough to react and combine. No fossil records that early survive to confirm it, and the idea remains a careful guess rather than a settled account. Still, the image holds a certain rightness. The same rhythm that fills a child's afternoon at the shore may have helped write the earliest chapters of life itself. Rising water brings more than the sea itself. Every incoming tide pushes nutrient-rich water up from the ocean's depths into the shallow reach of coastlines. Plankton, minerals, and dissolved organic matter ride along with the flood, feeding the base of an entire coastal web. Fish, mollusks, and filter feeders wait for this delivery as surely as any scheduled meal. The tide, twice a day, restocks the shallows without anyone asking it to. Retreating water carries its own cargo back out to sea. Every outgoing tide draws loose sediment, decaying leaves, and the remains of small creatures from the shallows toward the open ocean. What the flood delivers, the ebb quietly reclaims, a return trip as steady as the arrival. Estuaries depend on this outward pull to keep from choking on their own richness. Nothing stagnates for long where the tide keeps moving. Twice each day, this exchange has sustained coastal life across countless generations. Nutrients arrive, sediment departs, and somewhere in that steady trade, a whole ecosystem finds its balance. Marshes, mangroves, and mudflats have leaned on this rhythm since long before anyone thought to name it. No engineer designed this cycle. It simply persisted, tide after tide, feeding shorelines the world over without pause or ceremony. Long before any shore had a name, the moon's gravity was already pulling at this ocean. Continents drifted into new shapes, coastlines rose and vanished, yet the pull continued underneath it all. No map maker recorded the earliest tides. No language yet existed to describe them. Still, the water answered, rising and falling on a world with no one there to notice. The pull came first. Everything else arrived after. A faint hum drifts in from somewhere beyond the room, rises for a moment and fades again. It might be wind finding a gap, or a pipe cooling after the day's heat, or nothing you could ever quite name. Let it come and go without following it. Your shoulders can loosen a little more each time it fades. Your breath can grow long and unhurried, matching nothing in particular, needing to match nothing at all. At the water's edge, a person feels a rhythm timed by something far overhead. The wave arrives, retreats, and arrives again. And somehow the whole shoreline seems to be breathing in time with an object no one can touch. Bare feet sink slightly with each pull of water. It is easy to forget, standing there, that a small gray world 238,000 miles away is quietly setting the pace. That rhythm has never once paused since oceans and moon first found each other. Through every age of ice, every rise and fall of continents, every creature that came to the shore and left again, the tide kept its count. It asked nothing of the world and offered everything to it. Tonight, wherever you rest, that same pull is easing water up some distant beach and easing it back down again. Let it carry you the same way. Good night.